Imagine that the real world is like Minecraft and it's been divided into lots of little squares. It's like a chessboard which stretches out all the way across the horizon, and each one of those squares has its own little height, and that helps create the valleys and the hills and the rivers that make the landscape. As a scientist, the computer models that we use to understand the world around us also imagine the world like Minecraft, divided into lots of little squares. The size that we make those squares is determined by lots of different factors, but that decision can have some big impacts on the results that we get from our models. In this episode of Model Life, I'm going to tell you about some research that I've recently had published, where we looked at the consequences of those decisions on the results on models, and how it's possible to get the right answer but for the wrong reasons. Myself and my co-author Professor Tom Coulthard have recently had some research published that we completed at the University of Hull's Energy and Environment Institute in the journal Earth Surface Dynamics. Now that research is snappily titled Testing the Sensitivity of the Caesar-Lisford Landscape Evolution Model to Grid Cell Size. Now don't worry if this sounds like an alien language to you. Science publication is full of jargon, but I'm hoping that through this video I can break it down and describe it for you. Now if you've watched some of my earlier Model Life videos, you will have heard me describe that the models that we use to understand the world around us can only ever be simplifications of that world. They can't represent it fully. So by their very nature, they're wrong. But by being simplifications, we can run them at a much sped up rate. And that makes them useful because we can get quick decisions from them, we can get quick answers from them, and that can help us inform and make decisions. And one common simplification is to divide space and time into chunks, and then averaging out the values of all the properties within that chunk into a single value. And when we divide the surface of the Earth into these 2D squares, we give each square a single elevation value, and this can be based on either the lowest height in that square, the highest height in that square, or the average of all the heights across that space. It depends on the purpose that you're going to be using your model for. And these squares can be called cells, they can be called pixels, and if you're a games developer and you use them in a slightly different way, you might call them nodes. And the size that we make those chunks can have really profound impacts on the models that we use. Take how we model water across those grids. For each cell, the computer will be doing two sums at each time step, moving the water in the X direction and moving water in the Y direction. Now if our part of the world that we're representing, our model land, is represented by four 10 meter by 10 meter cells, at every time step the computer will need to do 8 sums. If we then decide we're going to double that resolution and use 5 by 5 meter cells, to represent the same space we have 4 times as many cells. The computer needs to do 4 times as many sums. So it's now doing 32 rather than 8 sums every time step. The computer is going to have to take more time to process all those sums. Now you might think, let's make this more efficient, we'll just use bigger and bigger cells. The problem with that is the bigger cells you use, the more likely it is that important details will get smoothed and averaged out. The more cells that you use, the more details that you can include. And the challenge for us as modelers is to strike that balance between including all the detail that we need for our model to run reliably, but also reducing it enough that our model can run efficiently. And this has been a challenge historically for games developers too. Just look at how the character of Mario has evolved in games over time as the computing power available to them has increased, allowing them to increase the resolution they're using and representing Mario with more pixels. So we looked at the Caesar-Lisford model as an example of a class of models called landscape evolution models. And it can be useful to think of models as translators. They take data in one format and they translate it or they transform it into data of another format which is more useful for people to use and make decisions from. Landscape evolution models will usually take information about the Earth's surface in 2D cells and convert that into predictions of how landscapes change over very long periods of time. Caesar Lizford does this by taking that data about the Earth's surface divided into 2D cells and using a time series of rainfall. So first it takes that time series of rainfall and it translates it into an amount of water that it adds to the model, and then it distributes this around the river catchment. Those volumes of water in each cell are then transferred into new cells, so it's translating that data into flows and into forces. It then uses those flows and forces to calculate where erosion or sedimentation will take place, which gradually changes the landscape over the course of the model simulation. What it's doing is it's simulating the processes of geomorphology. We ran our model representing our model land with different size squares, going from 4 meters right up to 50 meter size squares. And we used a small river catchment in northern Australia, part of the Tin Camp Creek system, as our experimental site. And what we found was really interesting. First off, the numbers of sums that the model was doing as an indicator of how long it takes the models to run did increase as we made those cells bigger. However, once we got over 12 meter cell size, that advantage began to drop off and we really didn't see any sort of computational advantage with the larger cells. We also found that the volume of sediment, kind of mud and rocks that's picked up by the river and carried out of the river system, remained the same even as we increased the size of those cells. And initially we thought, this is great because the behaviour of the model is staying the same. It's making the same prediction even with really large cell sizes. However, when we looked in more detail, we found that with the larger cell sizes, the representation of the river system and how connected it was began to break down. And this had some fundamental impacts on the behaviour of the model. In the model, this made things like water flows and floods and sediment being washed out at the end of the river system more episodic, more kind of spiky. The same amount of sediment was being washed out overall, but it was happening in less and less events. But these events were getting bigger, so we'd have much larger amounts of sediment being washed out in fewer events. And this is something we need to be really careful of as modelers. We can't just use that single number coming out at the end of our model to assess whether it's doing the right thing. If we had just considered that number, the volume of sediment coming out at the end of the river, we would have thought, great, the model is doing the right thing. However, when we dug deeper, we saw that actually the behaviour was changing. The reason why that number was being produced was different. Essentially what it was doing, it was giving us the right answer, but for the wrong reason. If we'd have just looked at that number, we'd have missed this change of behaviour. So in summary, what we found was that when you increase the cell size of the representation of the land in the model, some of those crucial details of the makeup of the river are changed, and this fundamentally changes the behaviour of the model and how it's eroding and how water is flowing around it. And this meant that we got given the right answer but for the wrong reason. And this is something that us as modellers should always be aware of. We should always test it, and we should always expect that it might happen. So thank you for joining me for this video and listening to me describe my research. If you have enjoyed this video or found it useful, please do click that like button, and also please do subscribe to the channel as well. This helps me a lot, it's a great encouragement, so please do help me in that way, I really appreciate it. But for now, stay dry out there.